Hello and welcome to our virtual Lunch and Learn. Today we're talking about Ethernet troubleshooting for motion applications. My name is Rachel Green. I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company. Presenting for us today is Kaz Viscontas, Systems Engineer at our Flint, Michigan location. Out in the comments section, ready to answer your questions, are Steve Sperry, Systems Engineer, and Nathan Nicholas, Systems Engineer Supervisor, both joining us from Madison Heights, Michigan. We'll also have a Q&A portion at the end for Kaz to answer your questions in more depth. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us. As you come in, please let us know where you're tuning in from in the comments section. I see Steve, Tom, Nathan, and Tom joining from Hawaii. Thanks for joining. As we continue to socially distance, we're happy to be able to host these live sessions on YouTube, making it possible for you to be able to join us from the comfort and safety of your own homes and offices. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist, and we'll be continuing this series every Wednesday at noon, so be sure to join us on your lunch break. For anyone just joining, welcome to our virtual Lunch and Learn, Ethernet Troubleshooting for Motion Applications. Let us know where you're joining from in the comments. We'll be looking for questions as you have them, while our presenter, Kaz Viscontas, takes a deeper dive into how Ethernet CIP Motion applications are affected by marginal or poorly engineered Ethernet implementations. Our specialists, Steve Sperry and Nathan Nicholas, will do their best to respond to your questions in the comments as we go along. We'll also have a Q&A segment at the end of Kaz's presentation to address some of those questions in more depth and to allow some time for any follow-up questions you might have. If you'd like to reach out afterward, or if you have further questions for Kaz, you can send us an email at mcmclive@mc-nc.com. Be sure to let us know which session you attended and we'll direct your questions to Kaz. We'll have that email address on the screen for you at the end again. And it looks like we have a number of viewers now, so Kaz, I will pass it over to you.
Thank you, Rachel. Again, thanks everybody for attending. I appreciate you taking the time to spend for this 7-hour presentation. So we're going to go over Ethernet troubleshooting for motion applications. It's only going to be about 45 minutes. Don't panic. So what I've seen in my 25 years with Mac and Mac is people doing a multitude of things on their networks. Some of them have a greater impact than others. Some, are devastating. Some are okay. So subnet sizes is one of the typical things that I see, where people tend to just add more and more devices on one big flat network. So you may see, 2, 3, 4, 500 devices, thousands of devices on one big long flat network, all with the same network, on the same network. And what happens is each of these devices is chatty, and everything is chatty on a network. And with the advent of the IIoT, Industrial Internet of Things, you see more and more devices that are capable to be on the network, so people want to put them on the network. And they put them on the same subnet. And if you do that, basically, there's a lot of bandwidth taken up in just servicing all of the chattiness that these devices have, talking to each other and to their switches. So generally what you want to do is segregate your network into subnets. That's why IT folks do that. They separate their networks into hundreds of devices. That way also, if you have a device that is misbehaving and causing issues on the network, it's much more easier to isolate that device and troubleshoot it. Another issue is the traffic requirement of devices. So you may have an installation where you have a machine on the floor that's an industrial network and it's got industrial I/O talking to a controller, where someone later on, everything's running fine, and then someone puts on some webcams on there or puts voice over IP on that same network. So that traffic, that voice over IP traffic or that video traffic is a different animal for that industrial network to handle. And sometimes other devices aren't equipped to handle that type of traffic, and things drop off. So that's another issue. Multicast versus unicast traffic, not as much of an issue these days as most things are unicast, but there is still a lot of multicast out there. And multicast traffic is actually treated as broadcast traffic when it hits an unmanaged switch. And if a device isn't set to handle the multitude of packets hitting its port based on a multicast broadcast, then it's going to fail. And we have devices that are doing that out there today. But multicast, for the most part, you don't see that as much these days. You will see that in a redundant network. So if I have two controllers controlling Ethernet I/O with an RM module, redundancy module between them, that has unicast or multicast traffic for all of its I/O. It has to be set up for multicast just for the failover. Switch configurations, I can't tell you the number of times that I open up a panel and see a managed switch there, and I ask what the IP address is of that managed switch. And one, they can't tell me what the IP address is, so nobody knows, so documentation of the network is poor. Or two, they know the IP address, and then when we go to log on to the switch to do some diagnostics, it's got the default username and password, and it has never been set up. So a managed switch that has never been set up is basically an unmanaged switch. That acts as an unmanaged switch. So configuring your switches properly is important. Protocols, knowing what protocols are on the wire is also important. You wouldn't want to put like SIP motion across wireless, for example, or knowing where your safety protocol, your safety on the network is going, making sure it's not coexisting with other traffic that it shouldn't be seeing. Managed versus unmanaged for troubleshooting, we'll get into a bit more of that. But basically, an unmanaged switch doesn't really give you a picture into the network at all. So you can still troubleshoot a network that has an unmanaged switch in it. You just have to go to each device that's connected to that unmanaged switch individually to see how it's handling its traffic. Whereas a managed switch gives you a look into what the whole network is doing. Everything that's talking to that managed switch, you can get an immediate statistics on what the port is seeing for those devices. Organically grown networks versus engineered. So many times you'll see some Cat5 going through the rafters of a plant, and that's their backbone, right? So it was put in 15 years ago, and they're just, as things go and as more and more devices are Ethernet capable, and they want to put these more capable devices on their network, things just grow and grow and grow, which is bad if you don't have the capacity for all of those devices. So an engineered network that is designed with fiber as the backbone or copper, but designed in such a way to accommodate this growth that we're seeing so that you can put on more and more devices later on, that's a much different animal than an organically grown network that is just over time, as things added onto it, has increased. And you'll see a lot more problems with an organically grown network versus one that's an engineered one. Duplex mismatches. So probably 80 to 90% of the issues that I see out in the field are duplex mismatches. So that is basically where one device is configured differently than the device it's talking to, and we'll go into that more and do some troubleshooting on that earlier on in the presentation. And another thing is infrastructure. So not paying attention to cable bend radiuses, using zip ties and really ratcheting down on a cable and compromising the characteristics of the cable, the noise characteristics of the cable, routing, putting your Cat5 or Cat5e or Cat6 in the same cable tray where you've got the VFD talking to its drive in that same cable tray. Cable length, 150, 175 meter cables that are going along that should only be 100 meters. Wireless, people putting in their own wireless infrastructure without doing a site survey, so they're stomping on other channels. All of these things are out there today, and they're pretty prevalent in the industrial area because, I mean, honestly, the industrial folks have some catch up to do with how to implement really well-designed Ethernet networks. Okay, so some useful commands. We're going to go through some of these. So IPConfig allows you to see how your NICs are configured. Ping checks for that network connectivity at layer 3, and we're going to do some of that too. Traceroute is really good for VLAN, so that's how many hops from your device to the end device that you can see. And we're going to do a demo of each of these. So this is a live demo, so I do reserve the right to fall flat on my face and blow everything up, because demos happen. Demos that are live are usually great. Okay, so I'm in a virtual image, and if I can spell, IPConfig. So I've got a VMware where I've got all my Rockwell software done because I'm too lazy to put it on my host, and it allows some separation, right? I can put various revisions of software on my different VMs that I need for whatever appropriate thing that I'm going to look at. So IPConfig/all gives me whatever adapters that I've got in my computer, and it gives me what the IP addresses are of those and whether or not it's DHCP, and it gives me the gateways and everything. So in this case, I've also got that on my VMware. When I start it up, it gives me the IP addresses as well. But IPConfig can be run on your host, it can be run wherever, and it gives you an immediate feedback as to what IP address you're connected to. So in my wired LAN, I've got 192.168.1.251, which will be important later when we start to troubleshoot. So that's IPConfig, and then you can also use, so ping, not point, ping is a command that you can use to check for connectivity with a device. If my numlock wasn't on. I've done this before, really, honestly. So I'm pinging that device, and it's going out, and it's finding that device. So it lets me know that I have connectivity on between my device and that one. And it means that my LAN is configured correctly, and that device is talking through whatever switches that I'm talking to. You can also do IPConfig with the -t argument, and this is going to continually ping that device. So it's going to send that ping out every second. It's going to give me how long it takes that device to get back to me, right? So this is useful if you're doing a wireless implementation and you've got some suspect connectivity areas, or if you're playing the slot machines, trying to figure out which port you should be plugged into on a switch, then this could give you that connectivity feedback when it does finally connect. And if I unplug my LAN connector, you'll see it gives you problems. And then I'll plug it back in later. I'll just leave this running for now. But this is a continuous ping. It'll continue to run for as long as we have that running. Okay, and now we're getting request timed out. And then once I plug it back in, it'll start replying again. So those are some useful tidbits to use. Another tool that I use a lot is Wireshark. So Wireshark is it's a free download. It's a packet capture tool, and it helps you basically get all of the information that's going along on the port that you're connected to, and it's very useful to capture all the stuff, especially if you can run your packet capture across the event that you're interested in. So if you've got a device that's intermittently falling off the network, and you're running Wireshark on that on a mirrored port, another plug for managed switches. If you're running Wireshark on that, then it can capture the event where you're having that device fall off the network. And then you don't have to be the expert to use Wireshark. Anybody can use Wireshark, but you can send the packet capture to an expert to have them diagnose exactly what was going on with the packets and why that event occurred. So we're going to hop into Wireshark. Oh, another useful thing is you can get an IP address of an unknown device with Wireshark, and we're going to do that now. So I have a compact logic cell here, an L36 ERM. And so other devices, some of these other devices you can see has an IP address scrolling across the screen. I know the camera's not good enough to actually see what the IP address is, but they have an LED display that's indicating what the IP address is. These 1769 compact logic controllers did not have that LED scrolling display, so it's kind of a guess as what the IP address is. It does have the MAC address on the front though. So the MAC ID, what the MAC ID is, it's basically a unique ID. It's supposed to be unique in the world. So unique ID for that manufacturer for that device to sit on Ethernet. So that's one of the demos that I'm going to connect to. I'm going to connect this flat ribbon cable up to my port after I start Wireshark. So I'm going to start Wireshark here. And so this is Wireshark. You can download it. It's an easy tool to download. So it gives me a list of all the adapters that I have on my computer. There's a lot because I've got some VMware images running. And so this Ethernet one is my wired port that I'm going to be plugging into. It's got no traffic on it right now. The Wi-Fi does because that's how I'm talking to you guys. But so the Ethernet port, if I double click that, now it's actually capturing packets on that port. I have nothing plugged in right now, but I'm going to now plug in that L36 ERM. I'm plugging it in. It's capturing some data. As soon as it's done capturing a little bit, I'm going to stop it. So and I'm actually unplugging and plugging in the other port for some other stuff. But so now the packets that I just now captured, I'm not capturing anymore. So I just stopped the capture. And if I sort by protocol, the top protocol is this ARP, this address resolution protocol. So another thing I like about Wireshark is that it decodes the first 3 octets of the MAC ID into the appropriate vendor that created that device, right? So I see Hewlett-Packard. That's more than likely my notebook. So I'm only connected between my laptop and that L36 ERM. I'm not going through any switches or anything. So the Hewlett-Packard is obviously my laptop. The VMware is my VMware image. And this other image here, this other ARP request is this Rockwell. So that's going to be the L36 ERM. And this CEBAB7 matches the last 3 octets of the MAC ID. The first 3 octets are the identifier for Rockwell. Okay, and it's telling me that, hey, who has 10.10.10.21? That's itself. So that is the IP address of itself. So remember, my VMware had 192.168.1.251. And if you want, you can pause and rewind and go back and make sure I'm not lying to you. But so this 10.10.21 is the L36 ERM that we saw when I plugged it in. And that's just a quick. This tool also captures everything else that's on that network. So that few little bit that I had that plugged into, all of this stuff came through on that wire. And then when we go to exit Wireshark, we can save that packet. So if there was an incident that we were concerned with, we could send that off to an expert to diagnose exactly what that problem was, or we can just quit without saving, which is what I'm going to do. All right, so that's Wireshark. Very helpful for finding an IP address. Some other tools. So rslinks and the vast majority. This all is a bit optimistic, but this Rockwell devices that live on Ethernet have web pages associated with them. And rslinks also has a lot of features built into it to help with diagnosing issues. So if we go back to our VMware image and open up Wireshark, you can see my ping is back up, right? I'm connected again because I plugged in the other cable. So it was down for a little bit, and now it's back. I'm just going to shut him off, though. So in rslinks, I have an Ethernet IP defined, and he sees these devices out there. And if I go and I look at the PowerFlex 525, for example, and I look at his module statistics and port diagnostics, I see that he's got some interface counters and some media counters. So you generally want to see all of the media counters to be 0. If you're seeing anything other than zeros in there, or especially if you see things incrementing as you go, that's a problem. Media counters are saying that there's an issue with the physical interfaces, either configuration or connectivity between those devices. So media counters should always be 0. I'm getting some FCS errors and alignment errors, so I already know that there's an issue with this, which, good, because this is a troubleshooting demo. So if we didn't have any issues, then it'd be a short demo. And we can look at the EN2TR and go to its module statistics and port diagnostics. And same thing, we have media counters and we have interface counters. So these are the packets that are flying through that interface, and then these are the issues that may be cropping up. And if we go to the web page, of that EN2TR, and we go to Ethernet statistics here, this is the same data that is on here. The Ethernet statistics, these media counters are the exact same numbers as these media counters here. But this gives you some more information. It gives you the full duplex and auto-negotiating, how it's auto-negotiated. If you go to the diagnostics overview, it tells you how heavily loaded the CPU is. So you can generally get more information out of the web page, but rslinks is a good central tool to be able to hop in and see exactly what's what on any specific device that's hooked up to your rslinks. Okay, so those media counters that I was referencing, those media counters are very important. We're going to take a quick look at what each of those really means. So alignment errors, any packet that's on the network is supposed to be a byte count, a multiple of 8. So 8 bits is a byte, and if you don't have a byte, even if you have the uneven byte count, you get an alignment error. So those are caused by duplex mismatches, which we'll get into later. They're caused by cabling issues. Noise can hit these alignment errors. A lot of times you'll get alignment errors that also propagate other interface counters. Maybe a frame check sequence error will be an alignment error as well. So noise is very prevalent for alignment errors and duplex mismatches. FCS is the same thing. It's kind of like a cyclic redundancy check for a frame. And if it doesn't pass that, then it throws an FCS error. So if you get an alignment error, you're also going to get an FCS error. So there's 4 collision counters in the EN2TR that we were looking at. And in general, in the past, collisions used to be okay, because in the past we had things called hubs. They were basically 10 meg half duplex hubs, and hubs are bad. You shouldn't be using hubs. If you have a hub in your network somewhere, you should disconnect it, replace it with a switch, take it out and start a bonfire. Don't cook over the bonfire because there's probably toxic fumes in there, but hubs should all be thrown away and burned. They're not useful. Basically what it is a packet shows up on the wire of a hub, and all the other wires in that hub duplicate that same packet out. And they only talk half duplex. So half duplex is like a walkie-talkie, right? So if I key up a walkie-talkie, the other person on the other end of that walkie-talkie can't do anything until I release that key, right? So I can key up and I can talk and he can listen, but I can't hear what he's saying until I unkey and he keys up. So half duplex is bad. They are the #1 cause of collisions, but collisions can be other things as well. Anyway, there's 4 counters for collisions. There's single collisions, multiple collisions, late collisions, and excessive collisions. If you have any collisions in your system, you have an issue. So half duplex, whatever, you shouldn't have any collisions in a well-working, well-defined, well-configured system. Okay, so collisions are bad. Hubs are bad. SQE test errors, that is kind of a holdover from the days when we had the 15-pin AUI connector that you would plug into the front of the port, and then that would have an RJ45 that you would plug into it. That was the transceiver. The SQE test errors tests the signal between the NIC card and the transceiver. These days, that transceiver is integral to the NIC card itself, so this SQE test error is kind of not a thing any longer. MAC transmit errors. A lot of times you will see a MAC transmit error downstream from a duplex mismatch, which we're going to get into a little bit more. And it's if you get late collisions, excessive collisions. If it's not in one of those buckets, then it's a MAC transmit error. Carrier sense error. Here's where you would get this error is when you've got a flaky cable, or maybe you've got a cable in a cat track that's bending and it's starting to go, or on a robot arm that's flexing. As that cable starts to go, you're going to get carrier sense errors as that carrier sense drops and comes back. Frame too long errors. Basically, if you got jumbo frames on a network interface that can't handle them, you'll get a frame too long error. And MAC receive errors. A lot of times you'll see this on the forced side of a duplex mismatch where one is forced and one is auto negotiate. And we'll get into that as well. And again, this is where it's not counted in the alignment error or FCS error or frame too long is where you see a MAC receive error. Okay, so I have a troubleshooting demo here, and I've got an L73 controller, this guy, talking to port 1 of a Stratix switch, and then out port 10, I have an ETAP that is then connected to a device level ring on which is an L18 that is controlling a 525, and this 527 is controlled by the L73. Now, in this instance, the L18 has SIP Motion enabled, has SIP Sync enabled. It doesn't need it to talk to the 525, but for my demo purposes, I wanted to show what some issues can be with precision time protocol stuff. So he is actually configured for he is actually.
Are you good? We can hear
Yep.
you. You sound good.
Okay, he is actually configured for SIP Sync, and for this demo purposes. Now the L73 is talking to the 527 as a motion axis, so he is also configured for SIP Sync. Okay, and I can do a quick pan with the camera. So that is that demo. So here's the L73 talking port 1 of the Stratix. Here's the Stratix switch. He's talking to the ETAP. ETAP is talking on the device level ring to the L18 to the both of the drives. Okay. So managed switches. Again, managed switches are great for troubleshooting. They have the ability to holistically see what's into the network and port configurations. And like I said, with Wireshark, you really need port mirroring and able to take advantage of that. And we're going to do a quick demo on Stratix. So here's a Stratix switch. I've logged in already. And basically, right now, this dashboard lets us see that we have a problem on port 1. That's where the EN2TR is talking. And it gives us some utilization of the switch, how it's looking. If I go to monitor and do port statistics, I can see that that port 1 has got a lot of packets flowing through. Port 7 has some, even though there's nothing connected to it right now. Port 10 has some as well. That's where the ETAP is, and this is my computer down here at port 16. What's interesting with port 10 is he has total transmit errors of 2270. So if I look at the transmit detail, I look and he's got late collisions and total collisions. Remember, collisions are bad, right? So transmit detail, let's see what's on the receive detail. Well, port 1 has got a lot of these undersized packets. Okay, so there's an issue there as well. So we have some issues on this switch. And we can go to port settings. And port settings let us see how the ports are configured and whether they're up or not. So this one's up and he's good. This one's up and he's kind of good, and he's up and he's good. So this gives us a quick view into how the ports are behaving. And we can also look at the smart ports as well. And we're going to go into a little bit more in depth into smart ports here in a second. Okay. So one of the things we saw on that Stratix was one of the ports was at 100 meg half duplex, and I'll show how that happened. So duplex mismatches occur when, so in perfect world, you have both devices set to auto-negotiate, right? And these auto-negotiating devices, when you first plug in the connector, they send an auto-negotiating beacon across the wire, back and forth to each other. And they're looking for that beacon on the other end, for the handshake. And that allows them to determine how fast they can talk and whether or not they're negotiating in full duplex or not. When you have one side set up as auto-negotiate and the other side set up as forced, then the auto-negotiating side never receives that handshake beacon saying to auto-negotiate. So he is actually, by the standard, he is forced to go into half duplex mode. Now keep in mind, unmanaged switches can only be auto-negotiate. There's no way to go in there and modify port settings or anything. You just have auto-negotiating as your option for an unmanaged switch. So anything talking to an unmanaged switch should be set up for auto-negotiate. If you have something set up as forced 100 meg full on your device talking to an unmanaged switch, that unmanaged switch is actually going to be at half duplex, and you're not going to see that anywhere because there's no diagnostics on an unmanaged switch. You're not going to see that half duplex setting anywhere. You're just going to get errors. All right, and if you don't believe me, we're going to go through and we're going to prove that. Okay, so when we looked at our ports, when we looked at our port settings in the Stratix, it said that port 10 was set for auto half. Okay, so what's connected to the port 10 is the ETAP. So I'm going to look at the ETAP, go to module statistics with him, port diagnostics, and that's port 1. So that's one of the ports on the DLR. Port 2 is another port on the DLR. So they both have errors, although port 2 not as much. And then if I look at the device port, I can see that he's got some FCS errors and some MAC receive errors. Okay, so out of curiosity, I've been having some issues with my 527, so I'm going to look at the 527 and see what he says. Module statistics for the 527, which is what's being controlled by the L75 going across that ETAP. He doesn't have any issues, no media counter issues. He does have some in errors, 25 in errors, but he has no media counter issues, saying that he's completely happy with his connection back to the ETAP. And if I go to the EN2TR, which is sitting next to the L73 in the controller, he's actually the controller's Ethernet port controlling that 527. If I go and look at his interface connection, again, his media counters are fine. He's happy. He doesn't even have any interface counter errors. Everything is good. He's hunky-dory. So if I go back to the ETAP and go to module configuration, this looks happy. Everything looks good here. If I go to advanced port configuration, I can see, aha, he is set to 100 meg full. So the port on the Stratix, okay, so the port on the Stratix is port 10, and he is auto negotiate, and he had negotiated to a half duplex on the setting there. So I'm going to click auto negotiate on here, hit apply, sure, okay. And now when I go off this page and refresh it, now he's auto full. Okay, so one side was forced, the other side was not, and we ended up with a duplex mismatch. So we'll get to the presentation. ETAP was coded, hard coded to 100 meg full, and this resulted in a duplex mismatch with that 5700. Now, if I had forced the Stratix 5700 to 100 meg full, then they would have matched, and those collisions would have gone away, and that would have been fine. Now, keep in mind, in an unmanaged switch, you can't do that. And the other thing to note is that condition, those errors were not captured by the EN2TR or the 527 because their own connections were fine and they had no media issues, no problems. However, that 527 would have been faulting out had I had it running. So I don't have the 527 running. I have actually the PLCs in program mode. It's a little loud, and I didn't want to. I wanted you all to be able to hear me. I mean, unfortunately for you guys, but so anyway, it would eventually cause an intermittent fault, which is the most fun kind of faults to troubleshoot. All right, we didn't get into smart ports too much, but we're going to go into them now. So on a Stratix, you can basically assign a smart port to a Stratix, and what that does is it throws in a macro on that port to handle things like quality of service, REP, RSTP, and manages how that port behaves with respect to the traffic coming through it. So here's some words on smart ports. We got automation devices. So if you're connecting a single port automation device onto a Stratix, you would use automation device for that. So ENBTs would be that. A panel view with one port on it would be that. An Ethernet IO, 1794 AENT would be an example for that. Desktop for automation would be like a programming terminal that you have that has one operating system, including FTView. Virtual desktop for automation is what I have here. So that would be a computer running multiple operating systems. I have a host operating system and I have a virtual operating system. So virtual desktop for automation is what it should be configured for this PC to talk to that Stratix. Switch for automation is kind of misleading. You only use switch for automation when you're connecting your Stratix to another Stratix or Cisco switch. And that port on that Stratix or Cisco switch is also applied as switch for automation. You don't want to have any smart port configured if it's a managed switch other than a Stratix or Cisco, or if it's a managed switch that has REP, RSTP, any spanning tree protocol, anything, a resilient Ethernet protocol, anything that's got pathing technology to figure out the best path. Okay, you want no smart port for that. Multi-port automation device is where you would have an unmanaged switch, or maybe a lightly managed switch that doesn't have RSTP on it. That would be where a multi-port automation device would be. You'd also use multi-port automation device if you have like an ETAP or the EN2TR, for example. In my demo, it's an EN2TR. That's where you would have a ETAP or a multi-port automation device for that. And routers and wireless, those are for the appropriate Cisco routers and Cisco wireless, not for any router, not for any wireless. And you can also use a customized button, not only to assign port mirroring, but for doing VLANs. Okay, so we're going to do a quick look at smart ports. So if we configure and we go to smart ports, here is where there's basically a listing of your ports, and you can pick a port and then you can tell how you want that port to behave. So in this case, I'm going to say, I don't know, multi-port automation device, whatever. Or you can go in and you can hit edit, and for port mirroring, for example, I can port mirror and I can say, okay, so anything that's coming into port 10 or out of port 10, I want to show up at port 4. That's how that port mirroring would work. Okay, so port mirroring, very, very helpful for Wireshark and other capture tools. It allows you to see what's going on at a port that you're not physically plugged into. And you can only do that with a managed switch. Okay. All right, so that's some smart ports. So device level ring, DLR, what device level ring stands for. So we have a device level ring here with an ETAP with a bunch of drives. And I know it's a little difficult to see, so I'm going to put a little cardboard piece up there. Pretend it's a really fancy cardboard piece because this is, highfalutin. So what you see is, this is the ETAP, right? So here's the device port, and here's the two DLR ports. So you can't really read it well, but this says link 1 and it's flashing, and this says link 2 and it's solid. That immediately tells me that this is the ring supervisor. So this solid light is actually the port that's blocking traffic. So we're blocking traffic out of link 2, and link 1 is sending the beacon from here to here to here to here, back to here, and it's landing on port 2. And the reason I know that he's the supervisor is because that solid light says blocked traffic. And once I unplug the L18 out of the ring, now both lights are blinking, and the ring supervisor has done its job, and now it knows that it can't see that beacon on port 2 anymore, so it's sending traffic both ways because there's been a break in the ring. Make sense? So that's a quick way that you can see who is the ring supervisor. And if I can plug this back in, that would be fantastic. What's the time limit on our demo? I got 45 minutes to plug this thing back in. Okay, there you go. 25 years of experience to plug in RJ45. There you go. All right, so let's get rid of the cardboard here. So that's the DLR piece there, how you can figure out the ring supervisor. And if we go back and we look at our dashboard again, we saw that we had problems on port 1. Remember that? Port 1 was flashing, giving us issues. It's saying a faulty link. So if we look at the port statistics again, we saw that we had receive errors, right? Receive detail on that was a humongoloid number. So if we look at the EN2TR and we go to module configuration and we start poking around, looking in here, port configuration, this all looks good. We're manually set. It's all happy. We're auto negotiating, and he's negotiated 100 meg full, so that's all fun. Okay, so if I go look at the network, I see, ring fault. So apparently the EN2TR is also a ring supervisor. However, he is just talking to the 5700. He's going right from his port to the 5700, and that's where he stops. So some 5700s do have DLR capability, and you can have it sit as a member of a DLR ring. This particular one does not have that firmware and is not set up for that. So by enabling a ring supervisor, this 5700 is receiving these beacons at a very high rate, and that is what's causing these receive errors. So I'm going to unenable him as ring supervisor. And now when I go in here and look at this, and I go in here and clear the counter, now he's no longer incrementing. So that's and if we go back to here, we should see that he's a happy camper as far as that port's concerned. And he's a happy camper. All right, pretty cool. Okay. So EN2TR was set as a ring supervisor, will not connect it to a ring. This caused the beacon to arrive at the Stratix, and it had to use resources to deal with that traffic. Other DLR issues that can have a negative impact on SIP sync is when the DLR device itself is not a 1588 compliant device. All the Rockwell devices are 1588 precision time protocol compliant, so that's not a consideration for a Rockwell device. Another consideration is if you have a lot of devices on device level ring, then like 40, 50 devices, and your PLC and motion is real close to the supervisor, and that gets broken, and then you've got to go all the other hops back around to that servo drive, then that could cause potential issues for syncing to the master, causing jitter. Okay, so mentioned SIP sync. What exactly is that? It's precision time protocol is what that is. IEEE 1588. So I'm not going to read this all out, but basically what it is, it's a protocol, a way to synchronize clocks across a network. So there's some handshaking involved, and that allows the drive to close the loop with the PLC, so the PLC can say, I want you to be at position X at time X, and then the drive can say, okay, position X, time X, I will meet you there, and then they close that loop, and everybody's happy. That's how we get to do motion over Ethernet, is with this 1588 precision time protocol. So there's some components to it. There's ordinary clocks, and that's what's going to be in the end devices. So your servo is going to have an ordinary clock in it. The 527 is an ordinary clock. The L72 that I've got is an ordinary clock. EN2TR is an ordinary clock. Those are all ordinary clocks, right? And there's some ordinary clocks can be master clocks and some cannot, but we'll just go from that. So there's also called a boundary clock. A boundary clock is going to be one that's synced to an ordinary clock, a Grandmaster, and then it becomes the source to sync to for multiple other devices. So where you would use a boundary clock would be if you have 75 servos on the same network, 75 clocks trying to all sync to the same master. You would not want to have 75 servos trying to sync to the same master at a very high rate. So in that instance, you would have a boundary clock to segregate. Maybe you put a boundary clock for 35 of them and another boundary clock for another 35, and then it would then service those requests to offload the master clock from having to do those. And then transparent clocks. So transparent clocks are what most of the 1588 switches that you have that are enabled, those are typically transparent clocks. If you don't do anything to them, they are transparent clocks. So what happens is the boundary clock comes out, and then the transparent clock knows how long it takes to traverse itself, and then it adds that to the total time, and then it sends that total time to the next transparent clock, and so on and so forth, all the way down until it reaches the actual ordinary clock in your servo. So then it knows that it's got the time from the master plus all of the additional transparent clocks, so it sees where it should be time-wise in relation to what the Grandmaster was back when it initially sent the first packet. Okay. Where you would enable that is controller properties under the date time tab. You just click the box, enable time synchronization. This does give you some indicator of what's going on with the time as well. And one common mistake is not changing the EN2TR, EN3TR's time sync connection to time sync in motion. You have to have this set to time sync in motion in order to actually run virtual, to run Ethernet motion across an Ethernet network is by having this set to time sync in motion. Okay, you can also see that in the web page of the EN2T. You can see that that precision time protocol has been enabled and that it is synchronized to a master as well. Okay. Another tool in Studio 5000 is the ability to enable transmission timing statistics under the Motion Diagnostics tab. This is version 24. Later, it's a different drop down, and we'll go over that. But you check this box, and it gives you what the system clock jitter is. So high jitter can lead to sync control faults, especially if it's over the course update rate. Very bad. It also gives you the timing from the controller to the drive and the drive to the controller. Also, when you enable this transmission timing statistics, it also gives you those tags underneath that associated access in your controller tags. So then you can use these to put limits around them. Hey, I'm getting a lot of jitter over here. Maybe there's time to start looking at what's going on with the network, and you can capture that data for whatever troubleshooting use you want to use. So what causes jitter? Duplex mismatches cause jitter, network loading without the quality of service or internet group messaging protocol managed switch features. So without quality of service, if I've got a switch that doesn't have that, and I have motion going across one port and out of another port, and I've got a video stream that's coming in one port and out of another port with all these jumbo frames, the quality of service says I need to make sure that this guy is service first with the precision time protocol. That packet has a higher priority than the video stream. So quality of service really helps get that across faster. Master clock not keeping up with sync requests. That's where you would use the boundary clocks to help out with that. Motion group update rate is too fast. The rule of thumb is half millisecond per axis. DLR considerations, like I said earlier, if the ring is really way too long, there's a lot of hops, and you disconnect one, it may have more hops going the other way. And then clock issues, and we're going to go over that in depth in a second. So the biggest thing I see with clock issues is not knowing who the master clock is, and it changes without unbeknownst to the person implementing the system. And then the other cause of jitter is layer 1 Ethernet media issues, noise, using unshielded cable where you should be using shielded, that kind of stuff, routing it incorrectly, again, crimping it down too tight, band radius issues, all that fun stuff. So in general, if you have a motion-enabled processor and you go right from one of its ports to the servos, and these two red arrows here don't connect to a huge, massive other network, then you should be good to go. So if you've got a localized network that doesn't have a lot of broadcast traffic, then this is perfectly legal. Same thing here. You can go to any switch, unmanaged or managed, after that, and you should be fine, provided that these two red arrows don't actually encounter. Can you hear me? Can you hear me now? Okay,
Yeah,
this is
yeah,
really fun. Okay, so I guess my headset USB is starting to die, which is fantastic. Or you can put in a precision time protocol Stratix switch in between there, and this is all hunky-dory as well. Now that is all assuming that this red arrow is not connected to a massive network that's got a whole lot of broadcast traffic. We have tested unmanaged switches with a low access count with a Compact Logix 5370, and this does work, again, provided that you're not that you're managing the traffic coming in on the other end. So just so you know, you can use unmanaged switches, but it's just highly recommended to use a managed switch, and especially when that's 1588 precision time protocol. So clock issues. All right, we're getting in the stretch here. So I'm going to go look at the camera. Whoops, let's do this. Okay, so this camera, here's my L73. He's talking to that 527 over there, and let's take a look at what he's looking like in his controller. So we're going to go online, and we'll see who his master clock is right now. Okay, so if I look at well, first of all, let's look at the axis, and we'll look at the properties, and we'll see what he's doing. So I had duplex mismatches, so there's a whole bunch of alarms, clock sync alarms, so there's a lot of issues in there right now under the faults and alarms. So I'm just going to clear that log because we fixed the network, right? Our network is, according to everybody, our network is fixed right now. We fixed everything. Everything's great. So now if I go into the drive, and I go into Properties. If I go into Drive and I go into this Motion Diagnostics tab, it's telling me that, okay, things are good. I had a big issue at some point, but right now we're at 166 and we're at pretty small numbers there. So I'm going to reset these because everything is healthy now. Everything's happy. We're good. Course update rate is 500 microseconds. Everything's good. So let's look at the time sync tab, and this will tell us who the master is. So we really want the L73 to be, or L72 to be the master. However, it looks like the L18 next door is the master. Now, why is that? There's a master clock algorithm that goes and takes basically the more accurate the clock is, the better. And then it goes through these priorities here. These priorities are also tiebreakers. But if everything matches, i.e. if everything is default, then it actually goes down to the MAC address, okay? The identity of the device, the MAC address of the device. And in this case, the MAC address of this device, well, if we go to the controller properties, it'll be a bit more clear. If we go to the controller properties, we can see he's a synchronized time slave. If I hit advanced here, it shows that our controller is FFF and a bunch of stuff. It's actually not the MAC ID, it's the physical address serial number. And he is, FFF is further down the alphabet than E4. So that's why the L18 is the master clock. Also, another important thing to note is look at the date. The date is 1/6/1998. So if you flash the firmware of a controller, it's going to come in at January 1st, 1998 at midnight. That's what that's going to be. So I'm going to hop on to the L18 here. I'm going to go online with him. Hopefully. Now I reset the counters on the L72, the 527 drive. I reset all the counters and he's all happy, right? So I'm going to go in here. I don't like the fact that the date time is all wrong. So I'm going to go to the L18 and I'm going to set the date time. Okay, boom, he's set. Simple enough. Now it's today. Everything's great. So what happened back at our EIP machine? Well, we had a clock jitter alarm that went on and off. And the L18 is still our guy. His accuracy improved. So when you hand set a clock, its accuracy actually goes to 48. Okay. Now, if I look at our Motion Diagnostics tab, let's see what happened there. So all we did was change the time. Well, look at that. Controller to drive, 32,767, it maxed out, basically. And the clock jitter was a little bit high as well. So just setting the time bumped that clock. How many of you guys have HMIs out there that are constantly setting the time to the controller every minute, every 2 minutes, every 5 minutes? Each one of those is going to be bumping that clock for that. So now I'm going to clear the log again because everything's fine. We set the time, everything's good. But they're going to do some maintenance on the L18. So I'm going to unplug the L18. There, I just unplugged the L18. That's all I did was unplug it. Okay, we should see, there we go, clock sync alarm, clock skew alarm, clock sync, clock skew, bad things happen. Look at our clock jitter. 7,000 nanoseconds. Is that over the course update rate? A little bit. So had our drive been running, it's probably not running any longer, right? So the instance of just disconnecting the master because the master clock was in the other panel caused that to happen, caused that to blow up. So I'm going to replug this back in. And while he's going in, how do we change that? How do we fix some of that stuff? We don't want the L18 to be the master anymore. That's the wrong guy to be the master. I'm going to clear this log, reset the statistics here, and we'll take a look at time sync in the controller properties again. Date time, advanced. So right now the EIP machine is the master, right? Because the L18 dropped off the network, so it defaulted to the EIP machine. But as that L18 gets repowered back up, he's going to actually become the master clock again because his accuracy is better and he's got a lower identity serial number for that. And sure enough, we give it a second here. We'll pretend I've done this before. So now his accuracy is 49. So that's important to note because when you set the time you set it is your actually is at 48. But if you cycle power, then it's no longer considered the best accuracy out there. So it becomes 49. So if you're setting time on multiple controllers, whichever one wins, that 48-49 battle is going to be the last one that was powered up and clock set. So how do I say, screw the L18, I don't want him to be the master? I can set my priority of the controller to 1-1. Now he's going to win all tie breaks. He says, I am going to be the master clock. Right now keep in mind, I'm having issues with my controller or with my drive the whole time we're doing this, right? So he's now the IP master with a controller of 1-1 and everything is good. So I'm going to clear the log one more time. We're going to hit OK, and we're going to reset these transmission statistics. Okay, so everything is running great. Now, however, let's stay on this. Now, however, everything is running. We've set our priority to 1-1. Everything's great. Now, somebody plugs in the machine that 2 years ago, the OEM was adamant that his controller would not be on the network. So his machine, here's the rogue PLC that just got plugged in. He's been there 2 years already, but he was never hooked up to this network. Now he was hooked up to the network because they want to get some information out of the PLC, right? It's, you know, that's fine. If their network is designed to handle that, then great. They can get some information out of that. Everything is great. So what happens to our controller? Well, we got a sync alarm for some reason. Let's see what's going on here. It looks like we are no longer the time master again. So Rogue Machine had the same priority because maybe he ran into the same problem. And he said, middle finger to all the rest of you guys, I'm going to be the priority one. And since he was put in 2 years ago, his identity, he's got a lower serial number, right? So actually, counterintuitively, the older machine is going to be the more accurate clock as far as the Grandmaster clock algorithm is concerned, right? And again, we had clock sync issues, problems, you know, things are blowing up. The machine is stopped, 15,000 nanoseconds. So we had issues with these clocks jumping back and forth, right? So how do you prevent that, right? So the demo of the clock issue, the L18 was the master clock because his ID is lowest. If you change the time, that's going to cause problems. If you have another controller added to the network, that's a problem. HMI running the clock, that's also a problem. So how would you fix some of these issues? One thing that you can do is you can go into the Stratix or any 1588 precision time protocol enabled switch, and you can disable the port that you're interested in from having PTP traffic going across it. If you would disable that port, then the master algorithm is not going to go through that. Now, you're not going to want to disable the port where you're trying to run an access, but you can disable a port that is going back out to the outside world. So if we go back to our Stratix and we go to precision time protocol, so right now he is set to just be a forwarding. So we're going to do end-to-end transparent. And once we do that, you see that all these ports are enabled. Well, I'm going to disable port 7. That's the one that the Rogue PLC is tied to. So once I disable that, now I should be able to go into my controller here, and I'll see a bump again, right? Because you know he's got a new master again. He's his own master this time though. And at this point, now I've got a clock that I know is not going to be interfered with other stuff. If I was really paranoid, I would disable all the ports that I did not want to have that traffic on. So it would really just be port 1 and port 10 would be enabled, and the rest would be disabled, right? And that would ensure that whoever else is plugging stuff into my Stratix, they're not going to mess with my master clock algorithm. Okay, does that make sense? Hopefully. All right. So one thing that you can do to help with some network loading is and this is a feature that was put in version 24, is you're able to add multiples of the course update rate and put axes that do not need the really fine course update rate into these lower serviced course update rates. So if you've got a machine that maybe there's a changeover, it's the only time you use these axes, and it can be a nice slow, it doesn't have to have that high response, you could throw that into the alternate 2, which has to be a multiple of the base, but it could be at a much lower rate. And not only are you going to gain some impact, you're going to gain some advantage on your utilization of the controller, but the Ethernet traffic is also going to go way down as well. So here's a great sync troubleshooting flowchart. I wish I could take credit for this, but this is actually Rockwell's flowchart. Basically, is the system sync? No. Check the same sync capability. Owner applies to current firmware. Check that all devices are SIP enabled. If it is yes, but it's still not synced, then check the network layout. Use the Ethernet sniffer to see what the precision time protocol packets are doing. If they don't have the same Grandmaster, then you got to figure out which one is the Grandmaster. If they do have a Grandmaster, but it's not the correct Grandmaster, then you got to check the best master clock algorithm and see who is who. You might have to hand set that to get that all devices to be the same Grandmaster. And then are all of them synced correctly? If not, then figure out with precision time protocol what those packets are doing. Okay, so common issues of starting up. If you see an access state that stays at initializing, typically that's because you have a bunch of stuff in your motion group that maybe is not powered up yet. Just like Circos, all of the drives and access in the motion group have to be powered up and on the network. Okay, if they're not, then you can inhibit whatever motion is not yet there. So if you want to start up one drive at a time, for example, you can inhibit all the rest, and then as you're plugging them in, as you're adding them into the motion group, then you can uninhibit them and commission those drives as you go, or you can take them out of the motion group as well. Okay, so just like Circos, they all have to be powered up and then the network. Had to have a valid master clock, hopefully the same one. Similarly, if you've got a whole bunch of nodes in the I/O tree, like if you've got a lot of point I/O out there or compact block or whatever, and they're not physically powered up and talking on the network, then you may also sit at initializing because the controller is actually trying to find all those devices. So if he can't find the devices, he's spending a lot of resources trying to do that, and there's not enough resources for him to try to commission your actual servos. So in that instance, basically a good rule of thumb is inhibit anything that's not live, powered up, running on your network. Okay. Additional resources, there's a SIP sync troubleshooting guide. That's a knowledge-based document. There's some publications that are right here for you. And not only that, but Mac and Rockwell both have all kinds of services for consultation, design, remediation, networking, how to design your network. If there is issues with your network, they can go in and fix problems. And that's about all I had for you. Questions?
Thank you, Kaz. We don't have any live questions at this time, but we're going to give it just a few minutes and see if anyone has some follow-up questions for us.
Okay.
And while we wait, I want to remind everyone that you can always reach us at the email address there on the screen, macandmaclive@macandmac.com. And you can send your questions to us even after this live stream has ended if you're watching it as recording, and we'll pass them along to the presenter who can reach out to you directly with an answer. Just be sure to let us know which session you attended so that we can get your question to the right presenter. And with that, I'd love to thank everyone, including Steve Sperry and Nathan Nicholas out in the comment section, being our resources out there. Thank you, Kaz, for this wonderful presentation. And thank you to all of our live viewers, including those of you joining us on your vacations this week. Thanks for joining. We hope this session was informative and engaging for you. And remember to subscribe to our McNaughton-McKay YouTube channel for more industry content. We look forward to seeing you live again soon. Thank you, everyone. Have a great day.